right, welcome to your first screencast for nuclear chemistry. I'm going to go ahead and get the presentation started. I would suggest that as you go through this, you listen, pay attention, jot stuff down. You can stop and pause at any so that you can write stuff down as needed. You will most likely have to access the actual PowerPoint through the Edmodo folders at some point to get links to YouTube videos or other websites that are in there, and I will direct you to those or tell you where those are as time goes on. But this is your first screencast for nuclear chemistry. So we're just going to go ahead and get started. In this unit, we're going to cover nuclear radiation, radioactive decay, transmutation reactions, fission and fusion, as well as some applications of nuclear reactions. So you're going to see my mouse moving, and I will point out different things to you as we go through. So this first objective, we're going to cover objectives 1, 2, and 3 in this screencast. So describing nuclear chemistry, what's the difference between ionizing and non-ionizing radiation, as well as a little bit of the basics of radioactive decay. We're going to explain how an unstable nucleus basically releases energy. So that is objective number 1. Our essential question, how does an unstable nucleus release energy? You will still be taking notes in the Cornell note format, so I suggest you just set your notes up that way from the beginning. Put your objective in, put your essential question in, and like I said, today we're going to go through 3 different objectives. So, how does an unstable nucleus release energy? As I click through here. So nuclear chemistry is the area of chemistry that deals with changes in the nucleus. So this is very different than most other most other reactions that we see that deal with atoms gaining or losing electrons and forming ions. This is dealing specifically with the nucleus, so they don't behave like regular chemical reactions do. These changes are the source of radioactivity, nuclear power, and nuclear weapons. There's lots of energy involved in here. So as you can see down here, I said read page 805, go through table 25.1. We're going to do this in class, but just a little bit of background information for you on this. This is again a property of the nucleus, so you're not dealing with electrons like we do in traditional chemical reactions. In a natural environment, you cannot speed up, turn off, or slow down these reactions like we can with other chemical reactions. And things like temperature or adding a catalyst to speed up a reaction or an enzyme do not work on nuclear reactions. And that's the type of stuff that we're going to discuss here when we read page 805. So a little bit about radiation. The emission of, it means giving off energy in the form of waves or particles. This is a video you are going to have to watch on your own. So you are going to have to go to the PowerPoint and load this up and actually go to this YouTube video. So there's ionizing radiation and non-ionizing. Ionizing is the dangerous stuff. That's the bad stuff. That's what we want to stay away from. It has enough energy to knock electrons off of atoms, but it also has enough energy to damage tissue and your DNA. This is the cancer-causing radiation. Comes from radioactive elements, cosmic particles, and X-ray machines. Non-ionizing, it does have enough energy to move atoms in a molecule around and cause them to vibrate, but not enough to remove electrons. And it's not going to damage your molecular structures within your own DNA and your tissue. Examples, radio waves, communications, things like cell phones, and visible light, microwaves. These are things that are not going to be considered dangerous to us. This next slide has a table. Oops, went one too far. This table right here, I'm going to give you to put in your notes. But there are some questions from the quiz on here, so I suggest you go through and review this. And at least familiarize yourself with up here would be the highest levels, down here would be the lowest levels, and it tells you kind of what you should get each year or what you should get each day, or at certain instances when people are exposed to this level of radiation, what does it do? You will also notice this over here says do in class, so we're going to read page 806 in class and go through these paragraphs and perform these activities. We are also going to go through and review and highlight and chunk our notes and ask a question So we will do this in class, and you will get a diagram like this in class. But there are some questions on the quiz pertaining to this particular diagram. So make sure that you familiarize yourself with it. Okay, our next slide of radioactive decay. So basically, what is radioactive decay? The process, which is a transmutation reaction, in which an unstable nucleus loses energy, is radioactive decay. So this unstable nucleus has to get rid of this energy, and it's going to emit radiation in the process. It is completely spontaneous, which is why some elements and isotopes are stable, some are not. An unstable nucleus releases a particle or energy to become more stable. We're going to have a little discussion on unstable versus stable in class, and you're going to see what that means here in just a little bit. But the nucleus is literally going to lose energy by emitting an alpha particle, a beta particle, a positron particle, or some sort of a wave like a gamma ray. We call radioactive decay nuclear decay because it is the nucleus, or radioactivity. And then a material that would do this, we would say that it emits radiation or it is radioactive. This YouTube video, you're again going to have to go to the PowerPoint so that you can watch it on your own. And we are now ready for objective number 2. So differentiate between an atom and an isotope. This should be really familiar to you. We've already done this in our early atomic theory unit. Our essential question, how are atomic structure and isotopic notation related? I just want to remind you that you can pause this at any point and then continue. Remember that isotopes are atoms of an element, so they are the same element, meaning they have the same number of protons, but they have different numbers of neutrons, so you're changing the mass. The most common isotope is found by rounding the atomic weight on the periodic table to a whole number. So that's where you can look at the mass on the periodic table, round it to the whole number, and that's probably going to be the most common isotope. Isotopes are written 2 ways. Remember, we do it in hyphen notation, but also isotopic notation, where you have the hyphen notation, you have the element name, and then followed by the mass number, like helium-4. And then isotopic notation is where you have the mass number on the top and the atomic number on the bottom, and then the element symbol. We will do some practice with this in class, but here's an example of isotopic notation for helium. And here is another way. The atomic number at the bottom is optional, but I would encourage you to always put it there. So this practice right here on this whole page, I would leave, I don't know, probably 8 or 9 lines in your notes, because we're going to go through these practice problems. We're going to go through some of them on your notes, some of them on whiteboards. There is a video down here to watch if you need it. If you don't need it, you remember how to do this, you're fairly comfortable with it, you don't need to. But after class, if you're still struggling with working with isotopes, I suggest you review that. A little bit more about isotopes. All elements above 92, they're called the trans-uranium elements because they come after uranium on the periodic table. They are radioactive by nature. There's an unstable relationship between the number of neutrons and protons in the nucleus. There's a diagram we're going to look at in your textbook. But that is what makes something radioactive, is this unstable relationship or the unstable number. An element that is number 20 and below, so anything about calcium and below, they tend to have a 1-to-1 ratio of neutrons to protons, meaning the number of neutrons is the same as the number of protons, and they're much more stable. So we don't see as much radioactivity in those elements. But once you get above 20, you start to see this ratio of 1.5 to 1, and you start to have more neutrons than protons, and that creates a little less stability. And if that ratio is too high, you're so unstable that they just emit radioactive particles from their nucleus. And it's not something that you can really predict, but some elements are just more radioactive than others. So here's something I want you to do on your own. At this point, you can pause the video, review your notes, and write a question related to isotopes on the left-hand side. You're going to ask a partner when we have the discussion for this in class. So just stop it, kind of think about it a little bit, and then write yourself a question that you might still have or something that you might still need answered. We are going to do a lab activity related to isotopes in class after we do our practice. So our last objective is objective number 3. This is just going to be your introduction to the 4 types of radioactive particles that we've already talked about. We're going to summarize the effects of exposure, or the effects that they have on your body. But as far as writing the nuclear reactions, that's what we're going to do in Objective 5. So you're going to see this applied, some of the notations for this applied when we get to Objective number 5. Right now you're just getting the basic characteristics. So what are the basic differences? Well, an alpha particle has the symbol of, it has a mass of 4 and a number of protons is 2. The symbol we tend to use is this alpha sign. And shielded by means what can they, or what will stop them. So a piece of paper is literally going to stop alpha particles from invading your tissues. Beta particles, the symbol for them, they have no mass, but they do have a -1 charge, so similar to an electron in terms of size. The symbol is this beta symbol, and aluminum foil will generally stop beta particles. Positrons are similar to a beta particle, except it's a positive charge instead of negative, and the aluminum foil will again stop it. Gamma rays is kind of the most dangerous particle, or the most dangerous type of electromagnetic radiation. And we give it the symbol of gamma. I will show you guys how to write this symbol. And lead or concrete is generally needed to stop the penetration of gamma rays. So we're going to talk a little bit about each one. So alpha particles, you can again see the symbol. They're the least dangerous at external exposure, meaning if you're exposed to them, they're externally not going to do a lot to you because they can be stopped by a piece of paper. They do contain two neutrons and 2 protons, which is why they have a mass of 4. And then you see the 2 at the bottom. They're about the size of a helium nucleus. They can't penetrate your skin very deeply because they are so big, so a piece of paper or clothing will stop alpha particles. But once ingested, for example, radon exposure, which we're going to talk about, which is why you should test your homes for radon, alpha particles can be very dangerous. Even then, they don't typically cause radiation sickness, meaning like the vomiting and like the internal sunburn of radiation sickness. But long-term exposure do lead to, all sorts of lovely things like lung cancer. Beta particles, they're the same as an electron. A typical beta particle is given off when a neutron turns into a proton. So a neutron will literally turn into a proton, and that's when you give off a beta particle. You're going to learn more about that later. A positron is a proton that turns back into a neutron, and this electron is also taken in. So it's an electron with a positive charge, kind of interesting. You're going to learn more about that in Objective number 5. But beta particles are blocked by most solid objects, so aluminum foil, wood, plastic, but they can penetrate your skin and clothing. They're about 8,000 times smaller than an alpha particle, so they are more dangerous. External exposure can cause burns and tissue damage, along with the other symptoms of radiation sickness. Think having a sunburn internally. We will go over this diagram of cosmic radiation and beta particles, so you don't have to worry about reading that. We will go over that in class. Internal exposure, you definitely have more severe symptoms. Now the last one, the one that we associate as being dangerous when it comes to radiation, is gamma rays. It's the most dangerous form of ionizing radiation. Extremely high energy photons that can travel through most forms of matter. They have no mass and no charge. It takes several inches of lead or several feet of concrete to stop gamma rays. Exposure passes through the entire body, so it can affect all of your tissues from your skin to your marrow of your bones. And this can cause widespread systemic damage. We do use gamma rays. We expose a lot of our food to gamma rays to kill bacteria cells. That's how they can remove contamination from our food. But this is the reason why you are covered in lead when you have an X-ray or when you have a CT scan or an MRI. You are covered so that certain parts of your body are not exposed to excess radiation. This is also the dangerous radiation we associate with, atomic bombs. So this particular slide, I want you to pause so that you can make a quick drawing of alpha particle being stopped by paper, beta being stopped by aluminum, gamma being stopped by lead. Everything down here at the bottom we're going to do in class, but you will be doing a 3-2-1 summary over objectives 1, 2, and 3. The next 2 slides just take you through what you need to do before class and after class, or in class. And you can pause these as I don't have very much time left on my recording. So the previous slide takes you through what to do before class, and